So yeah, it's 5 p.m. So do you want us to wait a little bit, or we can start? Yeah. Okay. So yeah, first, Antoine, I want to thank you. So you will be the first speaker of this series of conference at the Shutdown Polymer webinars. So I'm very happy that you accept. And okay, so you can tell us more about your nice research you are doing. And okay, I will cut my mic too. Yeah, start.
A little bit on what we do around carbon dioxide as well. So this is the group. I'm going to try to highlight the people who actually have done the work, while I go through the presentation. But just in case I forget them, this is them, and I thank them very much for their hard work. So this is obviously a polymer webinar series, so I'm not going to spend too long on the introduction, and you're all very aware of the importance of polymers as material in our society. But the reason why we're doing all the research we're doing is because there's two problems or two challenges, let's say, associated with the use of polymers at the minute. The first thing is that they mainly come from fossil fuel resources, which you may want to preserve to do other things than producing polymers, for example. And the other one is also something that's been really hot at the minute is the increasing concern that there is around the environmental impact of our, let's say, misguiding use of a lot of polymers and plastic in the world. The fact that a lot of them, because they rely on such strong bonds, cannot be easily degraded and will persist a lot in the environment. So those type of challenges have been really well illustrated by a report by the Ellen MacArthur Foundation, which is called the New Plastics Economy. The fact that by 2020, the 2050, the share of oil that we will use to make plastic will be around 20%, and in the sea, if the status quo is conserved, then there will be more plastic in weight than fish in the ocean. So this is the headline figures that I'm sure you're well aware of. So our way to approach this problem and to do research around this is really to look at how we can use biomass to create new polymers. And one of the main tools that we're using is to use ring opening polymerization. And I'm going to discuss a bit also about the other work we've been doing around other polymerization techniques. So essentially what we're trying to do is to propose a third way to create our polymeric materials we want. And this is what people call bioplastic. We want to propose something which are going to address a need which cannot be fulfilled completely by natural biopolymers, for example, cardboard or cellulose or things like this. And also something that can propose an alternative to your traditional plastic, let's say, which are fossil fuel-based polymers, because we think that there's still a place for something that come from renewable resources, but that can have some nice applications. So this is one vision for sustainable polymers, for polymers that would be more durable and can be produced and used in a sustained way. So what we hope to achieve, and this is really the sphere where we operate, is really using biomass to create completely new monomers, to create completely novel, more sustainable polymers. Obviously, we're not trying to legitimize a throwaway culture where things will be able to degrade and go back pretty quickly to biomass. What we're trying to do is still create good materials that can be mechanically recycled or even chemically recycled. But when those options are failing, then those materials inherently, they can go back more quickly in the form of CO2 to biomass, their starting feedstock. Whereas you can also create all the same traditional monomers that we're using quite a lot to create non-degradable polymers. And this cycle here takes a bit more time to reform because you have less degradable polymers. This slide says exactly the same thing, so that's not entirely necessary. The only thing I want to say in this case is really to emphasize that we're trying to make things which have some application, that we're trying to keep in the loop for as much as possible before at the end we have several options to explore to go back to the natural feedstock, which is biomass, let's say. So the type of feedstock, and this is the title of my talk, right, is the type of feedstock we're really interested in are sugars. And there's a couple of reasons for this. The first one is that that's an extremely abundant resources, which is also extremely diverse. When you take all the natural polysaccharides, there's loads of them, and when you take the natural constituent of those polysaccharides, the monosaccharides themselves, there's a wealth of them from which we think we can do a lot of chemistry. This is obviously something which is not new. A lot of other people are doing this, and there's even some commercial polymers right now which are made from, which are derived from sugar feedstock. If, for example, you take things like PLA or polylactic acid, which is made from lactide, these ones are derived from the fermentation of monosaccharides, which create those lactic acid, which is then transformed into lactide. And you also may know all the polymers which are based on furan decarboxylic acid or FDCA, which is studied at the minute as an alternative for PET, for example. And there's also a lot of things that people can do using isosorbide, which is a dehydration product of glucose biosorbitol, for example. And this one is also something which is commercial. Right. The first thing I want to talk about is, before we move on to more, let's say, carbohydrate and sugar chemistry, is I want to talk a little bit about the work we're doing around lactide polymerization, because that when I prepared this presentation, this is something I've not really talked about before, and I'd like to highlight that a little bit. So PLA is a great material. It's been known for a very long time now. It is derived from natural feedstock. It comes from the fermentation of starch-rich crops. Even if you can get lactic acid from glycerol, for example, there's a lot of other ways you can get lactic acid. And this material is great because you can process it in a variety of ways. You can make some fibers, you can get some foam, you can make some pellets. And it's interesting because it is also an industrially compostable polymers, something that's not going to degrade in the natural environment, as far as we know, but under certain conditions will degrade a bit more than, let's say, your traditional polyolefin. And this is something we work around mainly on the catalysis side of things. And the challenge here, and that's something we work on with Professor Matthew Jones and Professor Matt Davidson at the University of Bath, and in collaboration with Total Corbion, for example. The challenge that we see in this really is to really replace the tin-based catalysts that are used currently in industry. And we have in the team 2 students who are working around this. We've got Neve and we've got Yoli, and I'm going to talk about a little bit about the work that Yoli's been doing around this. So the way we approach this challenge of replacing those tin-based catalysts for industry was to go towards heterogeneous catalysis. And we went this way because there have been a lot of avenues exploring the replacing tin by more abundant, more benign metals, and also some people looking at organocatalysis as an alternative to those metal-based catalysts. And the reason why, sorry, I should have said, the reason why people are interested in replacing those tin-based catalysts is because there's, even if those catalysts are approved, there are still increasing concern about the toxicity and also the effect that any residual catalyst will have in the polymer for the properties. And why, heterogeneous catalysis has been a great way and has been explored in a variety of organic chemistry reaction. In the field of ring optic polymerization and for lactide in particular, this has been clearly underexploited. And we thought that there could be some things that we can do in the area. So the first thing we did was, what type of support would we want to do this type of industrially relevant ring optic polymerization of lactide? And we thought about merifid resin and polystyrene beads, and we thought that could be a good starting point to try to build a complex coordination chemistry backbone for our catalyst. So what Yoli did is she purchased some of this merifid resin, which is polystyrene functionalized by this CH2 chloride group. And using a bit of chemistry, what we've done is basically transform it into an aldehyde and then put this type of motif here, this NO ligand here. She's done a variety of variants of ligand. So she's put some hydrogen here, some terbutyl here, even some chloride. And then when we had this type of ligand framework grafted on the polystyrene beads, what we've been able to do is to complex a lot of metal carboxylate precursors using a simple procedure of reflux in methanol. And we've been able to produce this wide range of metal complexes, of supported metal complexes. So from zinc, magnesium, copper, iron, basically everything we had in the lab. The way we characterize those things is a bit more tricky than when, for example, you design a homogeneous catalyst and you want to use them for homogeneous ring optic polymerization. And while we're well aware that those characterizations are not perfect, they were still good enough to make sure that we had made some of those complexes and some of them were supported on those polystyrene beads. One of the methods we use is IR, because you can really easily follow the vibrations of various groups, including this imine group here. And then once the metal is coordinated, especially because we focused on carboxylate, acetate, octanoate, this type of stuff, we could also clearly see those type of vibration in the IR. We did characterize those beads using EDX as well, and also visually by SEM. We could see that we had some nice bead. When we cracked them, you could see a clear difference between the core of the bead and the surface, which clearly had been functionalized. The first step in this project was to do really wide screening of all these catalysts to see if we had any hits in terms of the reactivity. And here you would see that we mainly focus on using what we call melt polymerization. So polymerization where we don't use any solvents, and we do this in the molten polymer, in the molten monomer, so in molten lactide, so 130. And we left it for 24 hours. Note that at the same time, we used a co-initiator, so a benzyl alcohol derivative. We used the methyl one because it's a solid and it's quite easy to recrystallize and to wait. And we used this combination to test the activity in the lactide polymerization. And you can see and we used to compare those results with the gold standard in industry right now, which is tin octanoate here, which is a viscous liquid, which is used for the homogeneous polymerization. And you can see here that from this initial screening, what we could see was that first of all, we had some good activity, which was nice, also some decent dispersities, and also already we could eliminate a couple of metals. And we really quickly focused on zinc and tin itself, actually, even if the first step was trying to remove tin, and I'll show you how in the end we've done that. So the second thing for us was to have a look at if the ligand structure had any effect at all on this activity, and the conditions of the reaction are here are exactly the same, looking at melt polymerization 130 for 24 hours, even if it's an overkill, and I'll show that in a minute. What we could see clearly is there was an effect of the ligand structures, even when supported. You could see that electron withdrawing groups that are thought to increase the Lewis acidity of the metal center were clearly showing some good effect in terms of the activity. And we could also see an effect on the carboxylate groups. We could see the acetate was much better for zinc, whereas the octanoate, or strictly speaking, that's the 2-ethyl hexanoate co-ligand, was actually better for tin things. However, bulky electron donating groups, such as the terbital, for example, didn't have a good impact on the activity. So we have located 2 good metals. We had an idea of what type of ligands to use, but now we wanted to know more. We had done this initial screening at 24 hours, but we wanted to know the actual kinetics of the reaction. And to do this, what we did was to look at in situ IR spectroscopy based on the vibration of PLA here and lactide here, to try to monitor the conversion and the production of lactide. And from this, using the initial rate methodology, for lack of a better word, what we can see here is that clearly the gold standard of tin octanoate is so much faster than anything we can produce here. However, our rate are not ridiculous at all. And you can see here in green, we've got our fastest catalyst here, which is this tin octanoate supported tin octanoate catalyst based on those chloro ligand, followed by the hydrogen version, let's say, in red here. So we're quite happy with this. What we've tried to do is really to use it under industrial conditions, to looking at what the effect of the temperature, and in that case, still monitoring the reaction by IR. What you can see is at 180 degrees, which is the type of temperature that people use in the industry. You can see that, yes, for tin octanoate, the reaction is still faster, and the reaction proceeds in 3 minutes. But in our case, we've got something that happened in 20 minutes, which is not bad, and it is quite well controlled as well, with really decent dispersities and a good control of the molecular rates. If you look at what we expect, depending on how much initiator you've put in the first place and what you get, let's say, by SEC. Something quite attractive with those heterogeneous catalysts is the possibility in the end to reuse them, because what we produce are essentially beads that you can pick up with tweezers or you can filter. So we had a look at this as well. Pardon me. And you can see here that reusing several times this type of catalyst, we could see a clear decrease, a steady decrease in percentage conversion of lactide, as well as molecular weight, for we think 2 possible reasons. The first one is there might be some poor dynamic exchange. Indeed, what we see when we reuse those catalysts, or when we analyze post-mortem after use those catalysts, is there's clear band of PLA. So it looks like there's some PLA stuck, if you will, to the beads. It could be because we don't wash the beads well enough, but we have done this quite thoroughly, so we were not sure what was this happening. And clearly, when you analyze by SEM the polystyrene beads, the first thing you noticed is even when we crack them, just to be able to see, what's the difference between the core and the surface of these beads, what you can see is clearly before and after use, the surface is quite different. It looks like we've coated those beads in PLA a tiny bit, and that may explain the decrease in reactivity. And we may not be able to, in the end, remove completely the PLA which is stuck to the beads, because we may be stuck, and this is into this step of the catalytic cycle. So this rely on the dynamic exchange between the metal and the PLA growing chains. And it is very possible that in the end, with our beads, with the type of system we're looking at the minute, then we're stuck here so that in the end, we cannot cleave really the PLA growing chain metal bond. Let's say that's one of the hypotheses. The other logical hypothesis is that there might be just some leaching of metals, okay? Which means that while we proceed during the catalysis, some metal species are lost. And in the end, while you reuse those catalysts, then it becomes less and less active, let's say. Keeping an eye on the time here. And we've confirmed this by doing some ICP-MS analysis of the polymer we produce. And this is the data which is shown in this table, which is worth looking at. So this is the amount of ppm metals that you would expect if you had 100% leaching under this condition of our catalyst. And what you can see here is the experimental metal leaching is still there. Well, it's still limited, right, compared to something that would be completely homogeneous and without any washing, but there's still an amount of leaching that we can't deny. So, because there was an amount of leaching that we could see, we tried to investigate, is the catalysis actually heterogeneous? Is it really the beads and the metal supported on the beads which is doing the thing? So we look at different things to try to confirm this heterogeneous nature. So we had a look at different batches, because that could be also an indication. If there's too much variation, that could be an indication that actually this is the amount which is trapped or leached, depending on how you wash it, that's the job. But when you look at different batches, the activity and the rate constant were actually quite similar. When we were decreasing the amount of beads, then we had also a reduction almost as expected of the rate constant, which indicate as well that it's likely to be heterogeneous. And most importantly, what we did is we removed the catalyst right in the middle of the reaction, which was actually a bit tricky to do, because remember that we were doing stuff in really hot molten monomer, and this was quite tricky. And what you can see here is when you remove the catalyst, the reaction does go on a tiny bit here, but not as much as if you leave the catalyst in. So we're fairly confident that something heterogeneous happens, even if it's not perfect. So if it's not perfect, why are we interested in this? Well, the first thing I need to say is that that's really something which is, I would qualify the first generation of this catalyst. This is not something that's been well explored at all, and I think there's a lot of scope for improvement. And even now with this quite imperfect, almost serendipitous catalyst ligand system, let's say, we already have a lot of advantages compared to other systems. So it's quite controlled. We've shown that the molecular weight is as expected. We've got good dispersities, limited transesterification, that we've confirmed by MOLDI. A good point as well is that there's no or limited epimerization, and this was confirmed by the melting point of the PLLA, for example, that we produce, which is quite high. And if you're looking at the NMR for the most specialist of you, this is, for example, something that's produced with our beads, whereas under those melt conditions, whereas this is, for example, something which is being produced by DMAP. So a typical, let's say, organocatalyst that you can use for the ring of depolymerization of lactide. We do produce the white polymer, which is not negligible. There's still minimal metal leaching in the polymer. Even on the unpurified polymer, we only have 300 to 400 ppm at the type of loadings we're using. And what we think as well, and that would be the next step for this type of work, is that this type of steady state, even if we slowly decrease the activity and the conversion of this type of catalyst because of various coatings and stuff, we do think that we see a steady state activity state that may be suitable for example, flow processes. So that's where we're going with this stuff. Now, and something quite important I forgot is, while we've tested this for PLA, and while everything that I've focused on is on PLA, the paper that we've published also shows that this can be used for caprolactone, for a lot of other valorolactone, a lot of other cyclic monomers, cyclic esters, lactones that can be used with these things. So the second part of my talk is going to try to show you how we are well aware of the limitation of PLA as a material and how we're trying to address this by building new polymers that are based on sugars as well, but which do not have this type of let's say, fermented motif, which is brought by the lactide. Because that's one thing, right? If you are an organochemist, if you look at this glucose molecule, you see all those beautiful chiral centers, things that you mostly lose when you ferment this into a lactide molecule. You lose a lot of diversity depending on the sugar you use a lot of tunability. Look at all those nice OH groups you could do a lot of nice chemistry with, and as a consequence you lose some application potential. That's at least what we think. A really crude and naive picture is just to look at the glass transition. If you look at PLA, the glass transition is what it is. There's no way, unless you do quite complicated chemistry, something that, for example, Hillmeyer and co-workers have done in the past. It is really hard to change the glass transition and the physical properties. So our idea really is really to try to make new monomers that use this wealth and this diversity of monosaccharides and try to use them to make new materials. More sustainable one that can be tuned to fit our needs, and that's going to be the remaining of my talk. Just a few precision. When I talk about polymers from sugars, that can mean different things. The first thing that can mean is polysaccharides and any mimics, for example, that synthetic chemists can make. And a natural polysaccharide, for example, would be this type would be the archetype of cellulose with this beta-1,4 linkages. And the way synthetic chemists have tried to replicate this is by studying, for example, the ring opening of things like 1,6 and hydro sugars. And these type of polymers, I've named them polysaccharides and mimics because they all relied on polyether bonds, let's say, that really mimics what nature does. And if you want to know more, there's this really good review by Greenstaff and co-workers in 2017 that look at all the type of polymers that chemists have done in this area. I don't know what happened here. Never mind. Another thing that people are talking when they say polymers from sugars, sometimes they mean glycopolymers. So polymers where really the sugars are not part of the polymer backbone, they're more pendant groups. And this has been reviewed now a couple of years ago by various people. And this can use a variety of chemistry, such as radical chemistry, ring opening metathesis, polymerization, etc. But that's not what we mean when we say we're going to make some polymers from sugars. What we mean when we say we're going to make polymers from sugars is we're going to try to incorporate the sugar's moiety into the polymer backbone, but combining them with different linkages, different comonomers, in order to create a variety of materials that have been published on the topic. And here are some examples of the type of stuff that people have done, including in Bordeaux here by Etienne, that relies on ADMET polymerization, which I'm going to talk about a little bit, but also on transesterification method here. But in this case, actually, this uses a reduced form of the sugar, which is the mannitol. More specifically, ring opening polymerization, because that's where we come from, that's our area of expertise, if any. This has also been exploited to do this type of polymers, including by the group of Greenstaff and co-worker with those polyamidosaccharides, or by Woolley and co-worker with those polyphosphoesters, and by Gross and co-worker with those polyesters, those natural actually polyesters made from the ring opening metathesis of those sophorolipids here. But because we had a background into carbon dioxide chemistry, our first idea when looking at this type of sugars, this is glucose, for example, was, well, can we make some cyclic molecules out of it? Can we make some cyclic carbonates so that we can use our traditional ways of ring opening monomers to make some polymers out of it? And I'll touch upon how it's not just about carbonate though at some point. The way you do this is when you have this type of diol motif, you take your a phosgene derivative, which can be phosgene itself, trisphosgene, it can be a CDI, carbodiimidazole, and it can be other methods. But what in our case, what we use, I'm not going to talk about this right now. We have this idea, but this was something that had been done in the past as well, and this has to be acknowledged. The first couple of examples of this type of structures had been done by Gross and co-worker, which made this 6-member cyclic carbonate from sugars, and in this case from D-xylose. And they made this beautiful monomer where you had this isopropylidine protected 1,2 diol motif here, which was really interesting to us because that could clearly be that clearly shows some functionalization potential. The only problem with this monomer, if there's any, was that the ring opening itself was a bit challenging, and this is certainly due to the less strained nature of this ring. Woolley and co-workers in 2013 also published this really nice molecule here from D-glycose, which solved in part the problem of the ring opening by looking at this type of really strained trans 6-member cyclic carbonates. But in that case, unfortunately, because those other OH group were basically stuck at the O-methoxy form, there was no functionalization potential possible. However, it must be said that further down the line, these things have been addressed, and this is the group of Karen Woolley again, where they've made a variety of those glucose or glucose derivatives, where here clearly they've shown that there's a lot of more chemistry that you can do once you replace those type of groups here. So our first target was, can we make this type of cyclic carbonate from mannose? And the reason why we wanted to explore mannose was because that's a fairly abundant sugar that you can get from a variety of whey sources, including some algae, some coffee ground, etc. And we thought that this would be the perfect monomer because, like glucose, this would produce a quite strange 6-member cyclic carbonate ring. And also that would have this isopropylidine function here that would be able to open the way to further functionalization. So that was our initial idea and our initial target. The first thing that we needed to do to create this type of monomer was obviously to take this species, which is one step from a commercial product, the O-methoxy derivative, or you can even do it directly from mannose using 2-step procedure, using methanol with a bit of acid and acetone with a bit of acid as well, which is not very difficult, let's say. And the first thing we wanted to do was to not use phosgene or phosgene derivative to do this type of chemistry, and we wanted to do CO2 because that was also a bit of our background, let's say. The first thing I want to say is that we're not trying to use CO2 in that respect to solve the CO2 problem. Clearly, these type of procedures are not meant to be a CO2 thing. This was just a way for us to use procedures that are less dangerous, let's say, than having students using a phosgene derivative in the lab. So that was the driving force. So in the literature, there's a couple of methods that people can use when they want to do this, when they want to use diols and transform them using CO2 into cyclic carbonate. There's some procedure by Tomishi and co-worker. There's a procedure by Dyson and co-worker. But obviously, the one I want to highlight is ours. Not because these ones are bad, but just because we really try to simplify at the extreme the way this could be done. This is the first procedure we've published, but the one I want to highlight is really this one, which is, let's say, the refined one, and this is work done by Tom here. This procedure is a quite robust one that we've tested on a variety of diols. And it works this way. You just mix a diol, even if in this case we took the easy path of having a bit of help with the topping goal effect. And by mixing this diol with 2 equivalent of base tosyl chloride on the CO2 atmosphere, what we can produce is a cyclic carbonate in quite good yields. Like I said, this is definitely not something which is environmental friendly. This is something which is safer than trash resin, but as you can see here, this is not optimal because you do create a lot of waste salts, but it works. And whether you use a schlank line or some CO2 from dry ice, even in wet solvent, you do still get good conversion for this type of monomer. The way it works, and I'm not going to spend too much time because I believe that's not an organic chemistry seminar here, but the way it works is basically you use the base to insert a CO2 molecule into one of the diol here. And once you've created this carbonate species in situ, what happens is the tosyl chloride create this tosyl ester here, which then becomes a really good leaving group and then ring flows like this. You can we've probed the mechanism of this reaction using different methods. We've done a lot of computational chemistry, and here's the the Gibbs energy diagram. But we've also looked at looking at enantiomer pure substrate to try to validate this hypothesis. I realized there's a big mistake here. This is clearly not an SN2 type mechanism here. This is more like an addition elimination here that will retain the stereochemistry, and that's what we've shown here. The SN2 type mechanism is more relevant to something I'm going to talk in a couple of slides. Anyway, enough organic chemistry. The bottom line is using this method. What we've shown in this paper is that we can make a big range of cyclic carbonate that includes things derived from sugars, things which are not derived from sugars, and that includes 5-member rings up to 8-member ring here. And we're going to talk about this one a little bit more as well. Anyway, this method worked. We're really pleased about this. It works to make the cyclic carbonate from the mannose. This is a beautiful crystal structure obtained by Georgina here. It was quite easy to make. We don't really require a column to get polymerization grade quality for this monomer. So we are pleased with the first step, let's say, of this work. The other question was, can we do ring opening of this monomer? Can we functionalize it? So to probe the polymerization, we resorted to an organocatalysis method here by using this combination of TBD, a guanidine base, and still our favorite 4-methyl benzyl alcohol. And what we've shown is that really quickly at room temperature in DCM, we had almost quantitative conversion, which is 1 and 2 hours. The NMRs are quite pretty. You can see here there's a clear difference between the monomer, really well defined, and the polymer, which broadens enough signal and clearly shifts of the relevant protons. And you can see that this is quite a controlled polymerization with dispersed state, and a living one as well. This is the SEC trace of the living polymerization experiment where we add more monomer at the end of the consumption of the first one. Using this method, various stuff to note. We can go quite high in terms of molecular weight, still retaining good dispersity. We can do melt polymerization, which can be interesting if anyone wants to use this in industry or without solvent. And we also confirm the structure by NMR and MRDTOF. And what the NMR showed was that there was a clear regioregularity in our ring opening polymerization, something which was not present in the previous D-glucose or D-xylose. This is a spectra, carbon and NMR spectra here. What we could see is that clearly there was only a head-to-tail linkages, which we think is a combination of sterics and also the catalyst that we use, because we don't see necessarily this when we use other catalysts. So that might be specific to using TBD, for example. In terms of properties, is this polymer any good? That's a legit question, let's say. We make all this way, all those type of procedures. Do we actually make something which is useful? Yes and no. The first thing to say is that this material is interesting because it really shows a really high glass transition temperature. That doesn't show any crystallinity, but clearly this has a really high glass transition temperature, which could be interesting. For example, if you think about copolymers with lactide, can you increase the TG of lactide by doing copolymerization? The answer is yes. The only problem with this material is that the thermal degradation is really close to this glass transition temperature, which clearly kills any type of application if you think about the window that you have to process this material and to make a natural object out of it. But the more important step was that we verified using a procedure that was initially developed by Gross and coworkers that we could deprotect those type of isopropyl group and make some nice OH, to free some OH, let's say, in the polymer backbone. So that was quite nice. And then I'll show you in a minute that we can functionalize further this. So let me check the time because I don't want to, the stuff I want to talk about. I don't want to talk too much about this C5 work. The only thing I'm going to say, and I apologize if I skip a lot of slides, and I'm more than happy that to share the slide at the end to anyone who wants them. The only thing I'm going to say is that we did the same type of procedures with C5 sugars, and while we were not able to cyclize directly those C5 sugars derived from, for example, DNA of deoxyribose directly, because we had a good knowledge of our CO2 cyclization reaction, we used it in a way that allows to go to take those ribose derivatives and using CO2 as a way to invert the stereochemistry of the sugar, to basically transform any ribose thing into xylose 1. And based on those two polymers, those two monomers, we now have a cyclic carbonate that we can polymerize as well. So we've done this with the thymidine one and with the ribose one. So I'm going to skip this quickly, and I apologize if that's what people wanted to hear. Those monomers are beautiful, and one thing I want to attract your attention to is that the anomeric position of the sugars has an influence, and you can see that for the deoxyribose, what we've shown that is that whether it was a beta anomer or the alpha anomer, we managed to separate them. We could show that their polymerization behavior was completely different. This one hardly polymerized at all, and this one did quite well, and we managed to do some nice copolymer of it. I've said in the first part of my talk that it was not just about CO2, and indeed what we can do as well is to use CS2 instead as the carbon dioxide analog to create what we think are the first transcyclic xanthate monomers that can, depending on the type of sugar cores you use, either produce some polyxanthate here, like in the case of the deoxyribose, or some alternating 3-thio or thiano-carbonate polymers here. So the reason why we do this is because we want to understand what would be the influence on the properties of replacing a sulfur atom by an oxygen one. But we're not quite there yet. However, preliminary work on this has been published, and that's the work from Eva here, and you can read about this in this article here. So I've talked about quite complicated structures, and you may have noticed that in our wealth of cyclic carbonate that we can produce using the CO2 method, there was this 7-member unsaturated 7-member cyclic carbonate, which in the end could also be derived from sugar derivatives, because people have shown that you can dehydrate this erythritol, which is a fermentation product of glucose, into this cis-1,4-butanediol, and using our procedure, we can transform it to a cyclic carbonate. And the idea behind looking at this monomer, and actually here, what this shows is that the nature of the base used in this case is quite important, the TMP being necessary to really obtain a clean monomer, rather than a bunch of oligomers, let's say. Anyway, digression over. The idea behind this stuff was really to have a monomer that you could polymerize in 2 different ways. You could do your traditional ring opening esterification of carbonation polymerization to retain the stereochemistry of the alkene here, or doing ring opening metathesis here to get presumably some trans alkene here. And we're interested in having a look at what's the effect on the properties, a bit like looking at how what's the effect of the stereochemistry of the alkene bond between natural rubber and gutta percha, for example. The first thing we verified was, does it work? Yes, it does work. Oops. We can ring open this using our traditional organocatalysis method and obtain this nice polymer, which clearly retains the cis stereochemistry of the alkene, and you obtain a really nice NMR spectra. Using metathesis polymerization and Grubbs-2 catalyst, what we get is under the best condition we could identify, we can obtain a 95% trans-selective polymer here, with still a bit 5% of this thing, cis thing. And what's even more interesting is that using some UV light and carbon and copper, so we can isomerize this one back to the trans one, but we get stuck at 52%, which is the best we can do right now, but this is still under progress. There's a clear difference in the way those things behave. As you can see here, this one, the cis polymer, is a nice white powder, whereas this one is a viscous oil. And this is confirmed when you look at the DSC data, where you've got something which is semi-crystalline with a small TG here that we could hardly detect at -24, but a clear melting event and a crystallization here at 115 and 70%, 72 degrees here. Whereas the amorphous, the rump method, polymer, let's say, is clearly amorphous with only a TG of -20. We've also shown that those polymers can be cross-linked using Fiolin reaction, but I'm not going to spend too much time on this. Because the thing we wanted to do was to show that we could use this type of reactivity manifold to make some ABA triblock to achieve thermoplastic elastomers using only one monomer. And the idea would be, and this is a graph that I've stolen shamelessly from a graphical abstract from Macro Letters here. The goal would be to achieve one single monomer, ABA triblock, where we've got elastomeric domains with our low TG that would be achieved using this trans motif here, but also either high glass transition domains here or crystalline domain that would be achieved using our cis polymer. And we managed to do this using a sequential procedure where we use this type of the diol itself as a chain transfer agent, using the ring opening metathesis polymerization in the first place, obtaining this telecalic polymer, and then proceeding to the organocatalysis ring opening transcarbonation polymerization to build those type of crystalline end block, let's say. And what we've shown here is that clearly we have limited transcarbonation and well-defined blocks. This was by carbon NMR and also by DOSI NMR spectroscopy. But what we can see as well, we can confirm the microstructure using MOLDI and also by DSC, because when you look at excuse me, the DSC trace, what you can see is that there seems to be clear phase separation with retention of the crystallinity of the cis block, but also a way more pronounced glass transition here, which we attribute to the glassy domains, the low TG glassy domains. Finally, if you allow me 2 more minutes, I'm going to talk about something else we've done, which is trying to address one of the problems that we've had. This is not well animated, is it? One of the problems we had with all the sugar-based polymers that we've been making, which is that they're really brittle, and in the end, they're not great materials so far. And what we wanted to do was to try to mix them with another monomer that would give more flexibility to the material. And to do this, we took some inspiration from the work of various people, including Teresa Reinecke, Henrik Ramayan, Etienne Gros, Sébastien Lecommandou, and Mike Mayer as well, which we use admit acyclic di-metathesis polymerization to create this type of monomer whereby you've got a sugar core here, but also more flexible chain. And this is the work by Marco here. And what we've done is we've taken our usual favorite xylose and mannose monomer, and we've built this using this undecanoic acid moiety here, which you can get from castor oil. And using these monomers, what we can do is polymerize them quite efficiently. Under vacuum, we get really high molecular weight, mainly transalkene, and we get really, we've achieved our goal because in the end, we get something which has a really low glass transition temperature, even too low, because in the end, even if we try to make films out of it, they're not easy to handle at all. One interesting bit is that there's a clear influence of the sugar core, not so much on the glass transition temperature, more a little bit more on the decomposition temperature. Those polymers we've assessed the stability as well, but that's secondary, let's say. And here we've used the trick to make this material more useful. We've used this trick of deprotecting those isopropyl groups into OHs. This can be quite controlled depending on the amount of triflic acid and water we do. And this has a huge effect on the properties of the material. What you can see here quickly is that while sometimes you have an enhancement of the glass transition temperature, the main thing is that you induce crystallinity for both polymers. You reduce thermal degradation, thermal stability, let's say, but this induced crystallinity is great because what it shows is that now from something that was like this, you create something which almost mimic the hydrogen bonding network of cellulose and create some films that you can actually measure the properties of, even if, as you can see here, they're not great yet. The other thing you can do, and that would be my final slide, is that you can functionalize further those OH groups. And this is something done using a bit of phosphine chemistry. We can functionalize further those revealed OH groups by reacting them with a chlorophosphine. Why would you want to do that, apart from the paper? Well, you could want to do that, for example, to create some macromolecular ligand for catalysis here. Think about the phosphine, how you could plug a metal on it, etc. Also to design some metal scavenging polymer, which you could degrade afterwards because of those ester linkages. We've confirmed that we actually can functionalize those things looking at phosphorus and proton HMBC NMR spectroscopy, but also looking at pure phosphorus chemistry, proton decouple in this case. And what we can see here is we've got 4 signals, and we believe it's because from something that initially was purely an alpha ionomer, what we can get is a mixture of alpha beta ionomer that explains the 4 signals that we see. Apart from those type of chloro or phosphine functionalization, which might be a bit, niche, let's say, what you can do is you can also start to explore how you can cross-link this using various things, using the reactivity of those OHs. And what you can do, for example, is react this with diisocyanate to get cross-link polyurethane. But that's really the preliminary stuff here. Anyway, I'm going to stop here. I'm not good with conclusions, so what I've done is I've just put randomly on the slide everything that we do. I hope I've shown you that we do a variety of research around how we can use sugars, which we believe are a really diverse and abundant renewable feedstock, to not only design new chemistry like what I've shown you with the CO2 method, but also create new materials, new catalytic strategies, including heterogeneous catalysis, to try to understand a bit more how we can use, we can make materials where we understand the structure property relationship in order to really get sustainable polymers that can fit our needs, let's say. Anyway, I'm going to stop here. I need to thank all those people that actually done the work. I may have forgotten some of them, but they're all lovely and they're all, I'm all thinking about them. These are the people that fund our work, and I'm really grateful to them as well, especially Roger and Suwarod here that funded my first position at BAF. And for the people who can't travel, I've decided to put a bit of pictures of BAF This is not the university. That'd be lovely. Bath is a city in the southwest of the UK. For those of you who don't know, this is our traditional PP equipment. This is me going to the lab in the morning. But Bath is known as Bath because it used to be a spa town for during the Roman Empire. And if you have ever the chance to visit it, just give me a shout and I'll be happy to give you a tour. This is the campus under the snow. This is the lake, and I'm going to stop there. Thank you very much.
Thank you, Antoine.
People have left that day.
There is almost 140 people still.
Okay, good. Etienne, can you tell me how many people?
140, and I think the maximum was 160.
Because my wife said there would be only like 5 or 10 tops. So I'm gonna win this. I'm gonna win this argument. Anyway, so, I'm happy to take any question if there's any.
Okay. So if there is any question, so you can open the mic and speak out loud. So otherwise there is few questions on the YouTube chat. I don't know if anyone want to start. Maybe I can first check the question on YouTube. So
yeah.
One question, and actually it's also one of my questions. So because you during the melt ramp of PLA, okay, you say you were able to remove the catalyst, the heterogeneous catalyst. So how do you do it? I mean, okay.
So practically, this is really difficult, right? So when you are at 180, this is not so much a problem because you are above the crystallization temperature of PLA. So you still have a liquid, right?
Okay.
So if you're quick enough, and that's essentially what you do, you just pour the boiling PLA on the filter, or you just with the tweezers you remove the beads. Okay. Well, of course, this is not something which is well designed at the moment, but you can think of, let's say, a reactor where you would have, a tap or something, some kind of a filter where the liquid could flow at the bottom, and you would keep and that's also one of the reasons why we're interested in exploring a bit more flow system, right, where something where we wouldn't have this problem of just filtering, etc. The other option you have, obviously, is, and it's something that we did for convenience, is you stop the reaction, you redissolve your PLA, you filter properly, and then you dry your beads. But that in the end, that's something for just on the laboratory scale, right? This is not something that would be viable.
Okay.
I don't know if that answers your question.
Yeah, that's perfect. Any other question on Zoom maybe, or I have a few more questions on the YouTube channel if you want. So yeah, another question. I will just go. There is 5 questions total at the moment. So so one question was on the your CO2 chemistry to form the cyclic carbonate.
Yeah.
Do you think this method could be adapted for N-carboxy anhydride to form N-carboxy anhydride from amino acid?
So we've tried, and we have failed. So that we couldn't do it. That's as simple as this. And we've also tried with O-carboxy anhydride to make OCAs, and likewise, in our hands anyway, this is not something we could do.
Okay.
There's other things that people can do with this method. You can make cyclic carbonates, but then how do you polymerize these things? So this works, but it needs to be 2 groups, it needs to be a motif which has two nucleophilic groups basically, and I don't think the the carboxylic acid part of the thing is good enough at this stage.
Okay, thank you for the. So moving on, still on this polycarbonate work. So one of the question was about the degradation because okay, we all know that PLA degrade to safe products. So do you have any intel about the degradation byproduct of your polycarbonate? Are they safe or is it biodegradable first maybe?
So we're not specialists of biodegradation by any means. The only thing we can do, um, and that we do in our labs, is if first of all, when we thermally degrade the product, we have a look at what comes out, right? And because you would have noticed that in our chemistry, sometimes we use a bit of protecting group or functionalizer group, let's say for our sugar moieties. And usually we try to stick with things like isopropyl, or things like so. And the reality is, yes, we do see those things popping off first. And so first, the first thing that comes out are acetone, then the carbonate linkages breaks off, you see some CO2, then there's sugars that don't fly, so we don't see them, but then you keep burning and then you get them in the form of CO2 and water. So that's when you thermally degrade them. If we look at biodegradation, and we haven't looked at it, the only proxy we have for this is we've had a look at how hydraulically they're stable or not, and also in the presence of enzymes. And again, we're not specialists of enzyme either. So the only thing we can do is basically put them in a medium. Usually it's an aqueous media. We don't try to dissolve it. We just put the block of polymer or the powder. We stir it in water, whereas it's under basic condition of acidic condition or in the presence of an enzyme. And then what we do is we analyze the supernatant. And what we see when these things degrade, they degrade under basic conditions, which is not surprising considering the carbonate linkage. And what you get is the sugar. That's what you get. And using the enzyme, exactly the same thing. For example, we've done tests with some lipase where you get out of in the solution are just the sugar.
Okay.
So that's all I can say. But again, don't trust me, take my word for it. But there's a lot more to be done on this.
So there is still a few questions on YouTube, and another question was actually about enzymes. So do you have, or did you already test the enzyme for the catalysis of ring opening polymerization, or what's your belief about it compared
No,
to
we
the
don't.
tin and this kind of stuff?
No, we've never done that. We've never done that because this is not part, and I'm not ashamed. That's not the right word, but this is not part of our routine of catalyst retest. And if I can go back in a way, what we do usually is we test a bunch of organocatalysts. We test the classic urea ones, the TBD, whatever. We test a bunch of metal ones. I'm going to show you, for example, this is the typical thing we test. For example, then we've tested with thymidine. The thymidine carbonate I didn't spend any time on, but which is published. This is the range of catalysts we do test for these systems. But no, that doesn't include enzyme. But if there are people in the audience that are working on these things, and I think there's a really an added value to do this, we're more than happy to share monomers and do that.
Okay, and on your work on the rump of PLA, so you are supporting your catalyst on polystyrene beads. So is there any reason for this, or did you try other kind of beads, such as silica beads, which is
So yes, so it was a really conscious choice of using polystyrene beads. It's because, like I said, there's very little work that's been done on on heterogeneous polymerization for lactide or whatever, decalactone, you name it. But because the people who've looked at this are more traditional heterogeneous catalysis people, they've looked at metal oxide, and that including, you're absolutely right, that including silica.
Yeah.
And what people have shown is that you would need to quench or to functionalize your silica, so you lose the acidity of the OH groups, so that they don't act as a chain transfer agent or as a to kill the ring opening basically. And that's the reason why we went for polystyrene as an inert material. It doesn't mean it cannot be done with other metal oxide that will not show any type of acidity, but our reasoning was we need a support that doesn't have any acidity, that would not interfere with the ring opening.
Okay, but yeah, just it was one of my question in heterogeneous catalysts. They are using also silica beads because they are able to break apart during the polymerization in order to prevent the quenching of the catalyst. And in the case of polystyrene, it doesn't look it's the case. And at the end, basically, you are coating your polystyrene, and maybe you are just quenching your catalyst sites. No?
Yeah, you would, and that's what we said. The system is not perfect. We needed to quench them so that we exchange, so that we release it. However, what we think about is if you use this in a flow system, then you would not need this type of the activation of quenching thing, because you would rely on the dynamic exchange, and that may well necessitate a better system. But I think there's some legs in this, in trying to get something that, like you said, doesn't need either a quenching step or a step where the beads are destroyed. But silica beads, that's an interesting one. Maybe we could look into this.
Yeah, or alumina, or this kind of series.
Yeah.
Okay, I have two other questions. So if you still have time.
Yeah, I do.
Okay.
I have nothing else.
So you are saying that the hydroxy group creates some crystallinity in your polymer when you do the deprotection. But do you measure or know if there is some hydrogen bonds?
We don't know. We don't know that, and this is not something we've measured.
By infrared, maybe? No, I don't
know. No. I'm going to say we haven't done this, and maybe we should have. What needs to be said about this is once you deprotect to a certain level, clearly they become really, really insoluble.
Yeah.
And the only reason why we said there's some hydrogen bonding, and we haven't done the IR like you suggest, is because that really reminds us of cellulose and how we need to go to ionic liquids and things like this to really get it back into solution. But yeah, you're right. We should try to quantify those hydrogen bonding networks. Okay. And you would do it by IR.
Yeah, maybe by IR. I don't know. At least I will check if I.
That's a really good suggestion.
One last question on YouTube. Maybe there will be more, but the last question at the moment is okay. What's your point of view on lignin and wood pulp as a feedstock for polyolefins?
As a feedstock for polyolefins?
Yeah.
To make some type of styrenic
or polyethylene, I guess. Or...
I think that's something I need to say is, while obviously my research is around sugars and trying to make more degradable, or at least more more degradable materials and stuff, I'm really aware that this is only part of the solution, and that we still need the type of of polyolefins materials that we're using, just because they're incredibly useful and they can do things that other materials cannot do. If people can make this from lignin, so from a renewable feedstock, then that's great. I think you solve part of the problem, which is the reliance on fossil fuels. Then the only question is you have to think carefully about what happens once you've used the material, right? It doesn't solve the problem that those carbon-carbon bonds are intrinsically really difficult to break. So my problem would be, yes, if you take lignin, so renewable feedstock, to create durable material, but then let's think about how you're basically going to transform a renewable feedstock into something which is permanent. Is that the problem? Is that a problem or not? Maybe not. Maybe not if you design the appropriate recycling facilities, let's say. I don't know if that answers the question, but that's my view on it.
Yeah.
I'm all for it. I just we need to think about carefully about the type of material and how we use them. That's all, and that's a general statement.
Okay, so is there any question on Zoom? Maybe if someone can open his mic and ask a question,
or just type on the chat.
Yeah.
I can see the chat, so
Otherwise, we'll close the session. So yeah, but thanks, Antoine. I think it runs smoothly, and okay. Zoom did not shut down, so it's
yeah, and yeah, that's good. I don't know. You usually at the end of a talk, people applaud. I can't hear this, so that's really so I feel like I've done a really poor job. But anyway, if there's no further question, like I said,
maybe there is one mic on. I don't know. No, the mic.
No.
Okay, so I can upload if you want.
Like I said, I'm more than happy to answer questions by email and stuff.
So thank you again, Antoine, and okay, take care.
Yeah. Oh, wait, there's someone. No.
Thank you very much.
Is there a question?
No, just thanks.
Okay, thank you.
Yes, thank you so much. It was very great.
Thank you. Oh, now everyone's going to say thank you. You don't have to. Thank you. Good. Okay. Anyway, I wish the best to the seminar series. And thanks, Etienne, for organizing this.
Yeah, I would try to keep it going. We'll see.
Okay.
Okay. Perfect. So bye.
Thanks.
Thanks to you.
Thank you, everyone. Bye. Bye.